I guess I'll do the honors. It's a very great pleasure to have Anson Hook from the University of Maryland. Anson got his PhD at Stanford, then went to Princeton, then back to Stanford, and he's now a professor at University of Maryland. He's worked on just about everything that has to do with particle physics that might have something to do with experiment. Is known for many creative contributions, and he's going to tell us about another one here. So take it away, Anson.
Thanks for having me. Yeah, so today I'm going to be talking about sort of axion strings and sort of cool physics that you can do with axions, and in particular the axion strings. I guess some big picture motivation. So I think my overall goal or hope is very similar to many of you guys in that it's, at least on the experimental front, is sort of to find what's the ultimate UV theory of the universe, like what is everything. And so in this context, it generally means just finding all the particles that exist in nature and all of their interactions. So what normally happens is that to sort of learn about sort of UV physics, what you have to do is, well, we don't have the energy to create them. So we usually measure things in the IR, and we sort of make assumptions about intervening physics between where we can measure and where we hope to understand. And you learn something modulo these assumptions, and that's usually in the form of guts. So that's sort of the classic example, I guess, is sort of where you assume that there's either nothing between here and the unification scale, or at least everything comes in complete multiplets. And you notice that sort of the gauge couplings unify. So if you want to actually understand the ultraviolet of the theory, then it turns out you're very naturally led to topology, right? Because if you talk to any of our condensed matter friends, topology is all the rage these days. And so, and for very good reasons. The reason is that any topological quantity is extremely robust. And in particular, it's even robust to RG evolution. So if you can measure something topological about your theory, it is really telling you something even about the ultraviolet of your theory. And so you're very naturally led to just thinking about, can I measure something topological about my theory? And so the first topological effect anyone sort of has ever seen is the Aharonov-Bohm effect, right? So this is where if you have a flux, a magnetic flux, and you take an electron around it, the electron acquires a phase. And it's sort of, this phase that you acquire is independent of the path, it's independent of the mass of the electron. It's just a very sort of nice measurement of just the pure flux in this case. So the question is, can we do anything like this, but with particle physics, sort of the standard model first? And so the first thing you do is say, well, does the standard model have any topological interactions to measure in the first place, right? We have an experiment, let's say like Aharonov-Bohm. Can it actually measure any topological things in the standard model? And the statement is, well, there are three candidates for topological interactions in the standard model, right? These are the so-called theta parameters. So there's an FF tilde coupling, who in the absence of monopoles has nothing, does nothing. And in the presence of monopoles has the Witten effect. And so it basically tells you about the charge of monopoles. And so experimentally, we're out of luck unless we have monopoles. There's also the theta WW tilde, which can be field redefined away because of the B plus L symmetry. And so theta WW tilde is actually an unphysical quantity. We can't actually measure it. The last sort of topological object you can hope to measure is associated with the strong CP problem, where sort of this theta GG tilde, or in particular, you don't actually measure directly theta GG tilde, you measure some combination of its phase and the phase of up quarks and down quarks, happens to be small for some reason. And so again, very well studied subject. So in the standard model, you're sort of out of luck. Everything that's possibly topological has been studied before. And they've even tried to measure it. And so what you have to do then, if you want something topological, is go to beyond the standard model. And in particular, the topological interaction I'm going to be talking about today is a Tuft anomaly. So in particular, I'm going to be telling people today how you can go about and measure Tuft anomalies. Okay, so what does this look like in practice? So in practice, the axion or an axion-like particle has a coupling to photons of this form. And the anomaly, or the sort of Tuft anomaly, is the topological object, is this script alpha or script A here. And there's some other coefficients, let's say like alpha E and M, the angular field you associate with it. And of course, people have known in the past that this is a topological interaction, but it turns out to be really difficult to measure the exact value of the Tuft anomaly here, the script A, because what happens is when you measure this via particle scatterings and production of axions and things like that, what you measure is actually this combination here with 4 pi's and alphas are fine, we know those values, but it has an F here. And so this is the decay constant. And so this is annoying. In fact, usually they call this combination GA gamma gamma. They don't even write the Tuft anomaly in terms of the Tuft anomaly. And so this is annoying because, well, you can't actually measure the anomaly by itself. And it's also annoying because F here RG evolves, right, due to wave function renormalization of the axion. And so while this guy here, this anomaly, is RG invariant, what you measure is not necessarily RG invariant. And so you actually, to actually get at this anomaly by itself, you need to do a measurement that's independent of F here. And so if you have a topological variable, you do a topological experiment. And so like I had said before, the sort of vanilla first topological experiment we look at is the Aharonov-Bohm effect. And so let's see, can we actually construct an Aharonov-Bohm effect with axion strings? And it turns out strings are the starting place. So in particular, axions are an angular field, so that when you go around a string from 0 to 2 pi, the axion changes, the angular field changes by 2 pi as well. So these strings are just objects around which there's some topology as you go around it. It's the equivalent of the magnetic flux B field. And it turns out that there is literally an Aharonov-Bohm effect here, which is if you take a photon, a circularly polarized photon, and you move it around an axion string, it acquires phase exactly the same way that an electron acquires a phase when you go around a B field. And here, electron versus positron is determined by sort of a left-handed versus right-handed polarized photon. And so if you take photons around this, you get an Aharonov-Bohm effect that is, again, because it's a topological object sort of interaction, you measure the Tuft anomaly itself directly without any of the annoyance of a decay constant and things like that. So this is basically what I'm going to be telling you guys about today, which is how to use strings and an axion coupling to learn directly about Tuft anomalies, sort of this topological object. And in fact, this combination is even well motivated because lots of people have worked who have sort of thought about string theory have found that sort of axions and axion-like particles are a very generic prediction of these theories with a whole variety of masses ranging from as massive as 2 CD axions to essentially massless today. And so this is sort of a nice thing that what we're going to be talking about is not only teaches you a lot about the ultraviolet of your theory, but also sort of teaches you, well, is well motivated. Okay, so the general outline for the rest of the talk will be first, I'm going to discuss why this is a Millikan experiment. Basically, what do we learn from Tuft anomalies? In particular, I will argue that what you learn from Tuft anomalies is the quantization of electric charge. The second, I'll do some basic review of strings in the universe. So basically, how do strings evolve? How are they produced? And things like that. So some basic review of cosmic string theory. Then I'll sort of start talking a bit more detail about the signatures of the string, in particular this Aharonov-Bohm effect I told you about. It turns out to be very simple to derive it. And finally, I'll sort of talk about ways to actually look for this Aharonov-Bohm effect. All right, so the first thing is, what do we learn from anomalies? Basically, what is the payoff if we can actually measure this topological interaction called the Tuft Anomaly? And so script A here, this is sort of the coupling that we're interested in. And you'll notice that as you go around a string, right, this thing is topological, or it's like an angle. If you go around a string, it goes from 0 to 2 pi. And you'll notice that this interaction is not invariant as you send a over f to a over f plus 2 pi, right? This thing changes by, or essentially theta changes by 2 pi times 0 anomaly. So in other words, what the axionic coupling, this sort of Tuft anomaly, is telling you is about the periodicity of the electromagnetic theta angle. And so the question is then, what does the periodicity of the theta angle tell you? So in particular, you first ask, what is the observable that comes from the theta angle? And,
sorry,
yeah.
Sorry, this is Marcus. Can you just say a little bit more about how you're normalizing A here? Because right, I mean, the electric, the alpha is in principle an arbitrary normalization. So it's sort of not. How is A is there a canonical normalization of A relative to the periodicity of the coefficient of FF dual?
Ah, excellent. So this is actually another way to see how A has to do with electric charge, because we normally normalize this theta alpha E and M over 2 pi FF tilde so that the electron has charge 1, right?
Right.
You could renormalize things so that, or do a field redefinition such that charge the electric charge, charge of the electron is 3, and you'll discover that that theta angle is related to this one here by a factor of 1/9.
Right.
And so you could see if the original guy was 2 pi periodic, this new guy is not 2 pi periodic anymore. And so you can see the reason why this theta angle is ambiguous is because exactly to the fact that you can do field redefinition to change the effective electric charges of particles. And so, for example, you cannot do this for non-abelian gauge theories because G is fixed there. Like the coupling of a particle is always just given by its sort of representation, the number of particles there. You can never say this is 3 or it has electric charge 1 or 1/3. There's never that ambiguity. Yeah.
Okay.
Yeah, and sort of the approach I'm going to take to formally prove this, I think you could do what sort of similar to what you had said of trying to do a field redefinition to show that this has to do with electric charge, but instead I'm going to try to do the Witten effect to do it. But yeah, in principle, this, in some sense, my normalization that I'm going to choose is just that the electron has charge 1.
Okay.
That fixes everything. Electron has charge 1, and the string sends A over F to A over F plus 2 pi. Those two normalizations are enough to determine everything.
Right.
Yeah. So at least one way to use to understand the periodicity of theta is to use the Witten effect. And in particular, this is just saying the electric charge of a monopole is proportional to theta. This is basically Ed's formula here. And you'll notice that it too is not periodic in theta. So if you want the universe to be periodic in theta, then what you need is that as theta goes to its periodic value, that monopoles are exchanged with each other. In particular, that you have many different monopoles here, and that as theta goes to its periodicity, theta plus 2 pi over times the Tuft anomaly, 1 is exchanged with 2, is exchanged with 3, is exchanged with 4, is exchanged with 5, et cetera, et cetera. It's sort of, you just leapfrog along. And so what you see then, though, is that this periodicity is telling you about the difference in electric charge between monopoles, right? So the fact that the monopole sends one guy to the next guy along tells you about the difference in the electric charge. And so what you do then is just say, well, I know something because I know basically the charge difference between monopoles. And so, for example, what you could do is assume that this charge difference is equal to just the fundamental unit of electric charge. And if you did, you would see that basically the Tuft anomaly is just equal to the fundamental value of electric charge squared. More generally, you might not have, you might be actually exchanging 1 with 3, 3 with 5, right? You might be leapfrogging past some of these other guys a little bit. And so generically, what you can say without any assumptions at all is that this Tuft anomaly is just an integer times the quantized electric charge squared. And so because I had chosen the electric charge to be 1 for an electron, if you measure a fractional value here, you've already found that the electron does not have the fundamental unit of electric charge. So basically, the sort of values you might imagine aiming for this Tuft anomaly is 1, for example, for the electron, or maybe 1/9 for if down quarks had the smallest electric charge. And so, for example, if you measured a value of 1/25 or 1/37 or some other random thing, you're really discovering something fundamental about quantization of electric charge. Annoyingly, it's modulo an integer, but c'est la vie. Okay, so this is basically the payoff. If you can actually measure these Tuft anomalies, you really measure the fundamental value of electric charge. So at least to me, this is exciting. You're really learning about the UV of your theory. So how can we actually slowly get to where we want to go? So first, we have to describe why do strings exist, or how can they exist? And it turns out that there's a really, really simple way to produce strings in the early universe. It's called the Kibble mechanism. And it's basically the same way that pretty much every topological defect in the real world, for example, in metals, is formed by this mechanism, which is if you take the universe, you reheat it so that the U1 symmetry of which the axion is an angular field is restored, then you automatically get strings. Because what happens is as the universe cools down, each Hubble patch, or it's really each correlated region of the correlation length of your system, randomly determines its own value of A/F. Because you're originally sitting at the origin, there's no preference for any angular direction at all. And so when you cool it down, it just randomly chooses a value. And disconnected regions choose different values. So for example, you might get a 0, pi/2, pi, 3 pi/2, 0, 3 pi/2, 0, etc. And what you do is then you get strings by a complete random chance, right? Because here you'll notice you go around to pi and then back to 0. But here you'll notice you go 0 to pi all the way back to 2 pi. And so by random chance, you've generated a string. And so, for example, in superconductors and things like that, this is exactly how strings are generated. And in the early universe, that's also exactly the case. All you need to do is that the reheat temperature was high enough, and then you just inevitably get strings. It's unavoidable.
Didn't Hitoshi write a paper where he claimed that Kibble got this all wrong?
So he did it for second order phase transitions in the early universe. So I think, well, what I said here was first order phase transition. Second order, Hitoshi's, I'm not actually sure if he said Kibble got it wrong, but he definitely, at least as far as I checked when I looked at his paper, Hitoshi definitely got it right. I don't think I read the original Kibble paper carefully, so I don't know if Kibble originally got it wrong. But yeah, Hitoshi did do it for second order phase transitions. And as far as I know, that's sort of the standard lore for how these things are done. But the difference between that is just saying how many strings are being produced. I think that's the qualitative difference. And it actually turns out not to matter, as I'll get to in a moment. But I think the difference between first and second order phase transitions, for example, is that in first order phase transitions, the correlation length is essentially the size of the bubble that gets formed, which is roughly of order Hubble. Whereas in second order phase transitions, which is what Hitoshi did, it's actually much, much smaller, because it's sort of like literally cooling a metal through a second order phase transition. Eventually you're cooling it so fast that it doesn't keep in thermal contact with each other, and then it just forms these very, very sub-Hubble regions of what the correlation length is. Yeah. So I don't know the exact answer to your question, but as far as I know, what Hitoshi did is standard lore. Whether it actually is, I'm not sure. He's my standard lore, I guess.
Thanks.
Yeah. Okay, so what happens once you generate strings? For example, first and second order phase transitions gives you very, very different string abundances. And luckily, it turns out there's something called a scaling solution that people have found numerically, which is basically the scaling solution is there is a fixed number of strings per Hubble patch. So basically there are, let's say C is some value between 1 and 1,000. So let's say it's 10. That means in the early universe, very quickly these guys intersect, they chop each other off, they radiate axions or radiate gravity waves, either one, and they approach a solution very, very quickly where there's of order 10 strings, Hubble-sized strings per Hubble patch. And then as Hubble expands, they intersect some more, and then at the new Hubble, there are still about 10 strings per Hubble patch. So this is just, people have just simulated the universe expanding and strings, and they just found this numerically. There's also analytic reasons to expect it, but this is just numerically what they found. And in fact, what they did was they found it, and then they discovered there's a very, very small deviation from C being a constant. In particular, there's a logarithmic deviation for axion strings, at least. I think for global strings, people don't really know. They think global strings, maybe it might be gauged string, they might actually be a constant. But for global strings like the axion, which have logarithmically divergent tensions, they're discovering that the number of strings per Hubble patch is slowly growing logarithmically. And so it's not a sort of well-defined science yet, because it's really difficult to simulate a large hierarchy of scales. So they don't really know the answer, but they think that the proper value of C is somewhere between 1 and 1,000, and it's still a very open, active area of debate right now.
So it's not the case that log is somehow an RG log that you could tie like to the IR manifestation
No.
of the UV log or something.
So this log comes about because if you think about a string and an axion going around it, the axion is basically theta, A over F equals theta. And so if you integrate dr squared, 1 over r dd theta of the axion quantity squared, you see it's an integral d squared r over r squared. And you see that the kinetic term just the integral doesn't converge.
Yeah.
And so it really is just the tension of the solution is growing.
Yeah, but that's exactly, okay, it's all right.
Yeah, I guess it's sort of
exactly, that's
IR
exactly a kind of RG log that you might be able to control,
Yeah.
I don't know. Anyway, I know that's not your subject, so.
Yeah, I think the answer is people have thought about that, and it actually led to 2 different camps of people, some who said that C should be constant, some that said C should depend on a log. And that's why people just eventually went to numerics, was they didn't agree on the analytics, which I don't know why they didn't, but yeah.
Okay.
Yeah, but this is basically all you need to know about strings, is that there's a constant number of Hubble-sized strings per Hubble patch, between 1 and 1,000 Hubble-sized strings per Hubble patch. So this is basically all you need to know about how strings behave in the universe. So let's finally get around to the Aharonov-Bohm effect. So I'm going to sort of do a toy calculation because the more complicated one is not very enlightening. So what I'm doing here is basically just saying what happens if the axion field changes in time, not just space, but in time. It turns out including spatial dependencies doesn't change anything. So what you do is you just say, I have this new term in Maxwell's equations. So I just calculate Maxwell's equations for a plane wave photon, and in particular, put a circularly polarized plane wave photon. And what you see is that the normal dispersion, omega equals k, gets modified by the coupling to the axion for a little bit. And so in particular, if omega and k are not related to each other as normal, you've introduced a phase velocity for these guys. And so there's the normal speed of light phase velocity plus or minus this new axionic correction. And so if you ask, what is the difference in phase between the left-handed and right-handed guys over some amount of time, like 10 seconds later, you just integrate the phase velocity. Or more importantly, you integrate the difference in the phase velocity to get the difference in the phases. And you see that you just fundamental theorem of calculus. It depends only on your initial and final values of the axion field. And at this point, I'm going to make a slight transition between circularly polarized light to that of linearly polarized light. Basically, in nature, it is difficult to get circularly polarized light. So in practice, you have linearly polarized light. And so the question is just, how does this sort of change affect linearly polarized light? And it's a short calculation, you can show that a phase rotation of circularly polarized light is a polarization rotation of linearly polarized light. So in other words, instead of being polarized purely in the x direction, it gets rotated a little bit to the y direction as well. So that's going to be the effect I'm going to be talking about from now on, is just how linearly polarized light has its plane of polarization changed a little bit.
Sorry, can I just ask, I mean, is this truly a topological quantity, or it's a topological quantity only in some approximation, like here you're treating A dot as a constant and so on, you know?
It is a topological thing only in an expansion.
Yeah.
It is not a purely like honest to God topological thing here,
right?
Because I have done an approximation here where I take this square rooted this Taylor series it. And so it's a Taylor series in this quantity here.
Right. Okay.
And it turns out you can actually estimate what is the deviation, assuming, for example, you travel across the whole Hubble of the sky. And the error in this approximation is at the 10 to the minus 30 level, which is well below anything we can in practice actually measure.
But it's still not topological.
Yes, you are correct. It is, in principle, I am lying slightly to you when I say this is topological. It's just at leading order, it behaves topological.
Right.
But at subleading, no, it's not really topological. Yes. You caught me. Okay. So I don't think I saw any CMB people in the audience, but just in case, I'm going to make a quick apology. I'm calling the polarization rotation theta, and the CMB standard for a polarization rotation, because they've looked at this before, is alpha. I'm not going to use that because I have another alpha called alpha E and M, and it'll get confusing because you get equations that are sort of like alpha equals alpha later on if you sort of use the CMB standard. So anyways, so let's talk about strings, the Aharonov-Bohm effect, right? Because strings are an object around the axion goes from 0 to 2 pi. And so let's say you take a linearly polarized string around, linearly polarized photon around your string and ask what you get. Well, again, your initial and final value are different by 2 pi f. So what you see is that the polarization rotation is just the Tuft anomaly times alpha E and M. So in other words, depending on your prejudices for what Tuft anomaly should be, it should be either 1% for if it's the anomaly is 1, or maybe 0.1% if you think the down quark. Okay, so of course, photons tend not to go in circles. So this is not the actual physical thing we're going to be looking at. So there are two physical things you can look at. One is if you shine on an infinitely long axion string, you just shine light on it. Light to the left of it goes from 0 to minus pi, and the light on the right of it goes from 0 to pi. And so it's not the full 2 pi, so they each get half the rotation, but one gets a minus sign because it's 0 to minus pi. And in particular, the jump, if you're looking along from the left to the right as you scan, you suddenly notice there's a jump here, and that jump is just the anomaly times alpha E and M again. The other situation you might imagine is that strings sometimes form loops, and you can ask what happens in this case. And if, in this case, what happens is if light goes through the loop, you get a phase whose sign depends on the orientation of the loop. And if you miss the loop entirely, you just get no phase. So if instead you have a loop in the sky and you're shining light on it, then everything inside will be rotated by a phase. Everything outside will be untouched. Okay, so those are the two physical things I'm going to be talking about today, of just how to look for these two effects, either a line in the sky or sort of a loop in the sky. So how do we look for these things? So it turns out the CMB is a great way to look for these guys. It's not the only way, but it's going to be the first one I'm going to talk about. The reason why it's nice is that the CMB basically shines light on everything, right? If there's any strings at all between now and the surface of last scattering, when the CMB was emitted, the CMB flew by the string and got rotated by it. And the CMB is also nice because it is a linearly polarized light source. Or at least there's some fraction of it that's linearly polarized. It's mostly unpolarized, but due to Thompson scattering, it actually has a small linearly polarized bit that we actually find extremely important. And so that means using the CMB, you can just look for these polarization rotations. And so there's two ways to actually do this. The first is basically every CMB person's favorite way to look for anything, which is to Fourier transform it. Fourier transform the 2-point function in particular and do a power spectrum analysis. So what they do is they just take the sky, they take 2-point functions and Fourier transform it in the 2-dimensional Fourier transform. The other way you can do it is sort of what I said before, that there's these discontinuous jumps if you go across a string, and maybe these position space sort of searches can do better, because if you have a signal in position space, let's say like a line discontinuity, it's better to look for it in position space rather than momentum space. So Fourier transforming is not always the best way to look for stuff. It just happens to be the best way to look for inflationary type stuff, and so they're just used to it. So those are the two ways to look for it. And it's exciting because people have done this before. They've done the power spectrum analysis, but they have not done this analysis before. So that's sort of exciting to me because this actually points to a new search that they are not doing right now. Yeah, it's also exciting because there's actually an anomaly right now in the CMB polarization data, but chasing anomalies is not always the best course of action. So that's just a fun fact. Okay, so in principle, what's the way to do this? In principle, the best thing to do is to take an honest-to-God numerical simulation of strings, shine the CMB through it, and just obtain a sky map. In practice, that's impossible because they don't have the resolution to sort of simulate such a large hierarchy of scales. So in principle, you just shine light through a real numerical simulation. In practice, you can't do that. And so what we did was we did two toy ways of studying these things. We did a toy analytic way and a toy numerical way. Both of them are not expected to be exactly accurate, but let's see how that goes. So what you can do is you can just take the 2-point function here and just calculate it analytically. In particular, what do? We have to make some approximations because it's toy analytics. It's not even honest to God analytics. What you do is you just assume that these C number of Hubble-sized strings per Hubble patch are Hubble-sized loops with radius equal to Hubble. And you just say, if you pass through them, you acquire the phase. And if you don't, you don't. And you just integrate over all directions and orientations for these loops with the probability distribution set to give you just C strings per Hubble patch. So that on average, you have 10 strings per Hubble patch, or in this case, 10 string size loops. And so you can go through this. It's not particularly enlightening, really, but you integrate over directions, you integrate over the amplitude, make sure the number of strings at any given redshift is fixed to be, let's say, 10 strings per Hubble patch. And then make sure they go through the same thing, the same loop, otherwise they're uncorrelated and there's no correlation here. But one sort of particular place where you actually do have physical understanding of what's going on is if you're looking at the 2-point function in one direction, because what's happening is the polarization is undergoing a random walk, right? Because you have some number of strings between us and the surface of last scattering. And so you should just get step size squared times the number of strings, right? Because a random walk, they can cancel a little bit. And so that's exactly what you get. Step size of going through a loop, the polarization is the anomaly times alpha and m times the number of strings, which is roughly C times the log. The number of E foldings is this log. Okay. What we also did was sort of these toy simulations, numerical simulations, which are very different from the real simulations and actually also different from the toy analytics. Namely, what we did is we threw down an infinitely long straight string and we just said it's going to sit there forever. And then as time evolved, we slowly removed them to reproduce having a fixed number of strings per Hubble patch. So as Hubble expanded, we had to remove strings to make sure you still had the same number of strings per Hubble patch. And through this really fake coarse toy simulation, we've shown the CMB. And what I'm doing here is showing you what's the polarization map look like for, let's say, a C of 100. And you get some continuous looking nice distribution. If you have 10 strings per Hubble patch, you start seeing it's a little continuous, but there start to be these little lines that you can see. And if there are 1 string per Hubble patch, you just see that clearly, at least my eye looks at this and sees like the discontinuities are the most striking features. That's how I see anything in this plot. And so you can see that if there are very few strings per Hubble patch, an edge finder or sort of these position-based searches would be most sensitive. Whereas let's say C of 100, things are changing rather gradually. And maybe Fourier transforming might be a better way of looking for this sort of feature. Okay. So what we did then was, yeah.
Sorry, is there something, sorry, maybe I just want to understand this, because is there something that is making, if you have fewer strings, are they, in these two, let me ask this, in these two simulations, each individual string is sort of doing the same thing? In other words, It's not that they have fewer strings and they're stronger or something.
Yeah, that's right. Each string is doing the exact same thing. So I think the normalization of, let's see, minus 20. Yeah, you'll notice the normalization colors have changed though.
Okay, so you've kind of enhanced the effect. But in the case of lots of strings, it's more that there are so many strings that the edges are just getting blurred,
washed out
by the many strings. That's all that's.
Yep, that's all that's happening there. And
right.
so your experimental resolution
to just sort of show the qualitative features.
Yeah, that's right.
Okay, got it.
Yep.
Mm-hmm.
Okay. And so what I'm showing here is a comparison between the numerics and the analytics. And for reasons we don't really understand, they seem to agree very well. I don't know why, because they're very, very different. One is infinitely long straight strings, the other is sort of a circle. But somehow they agree, at least for small angles, pretty well. And so this black line is the theory. So they differ at large angles, but the black line is theory. And these other lines here are simulation, the toy numerical simulations for different values of C, 1, 10, or 100, and surrounded by their cosmic variance error. And you'll notice I normalized here to a random walk. And so you see that this sort of random walk interpretation of the total normalization is basically fits it entirely. So as you increase or decrease C, you get the exact same power spectrum, just enhanced by the random walk factor.
Sorry, I didn't understand what you're comparing. You mentioned these two, these different toy simulations, but what are you comparing them to? Each other?
To each other.
Just to each other, right?
Yeah.
Okay.
So it is still possible that the honest to God calculation has something drastically different. And the only reason why we expect that it might not is the fact that the sort of toy analytics and the toy numerics had very different assumptions going into it, yet somehow agreed with each other to very high, unreasonable accuracy. I don't think that they should agree this well, but yeah.
And I mean, the actual effect that you're looking at is not at all a Gaussian type of thing.
That's right.
So it's not captured by the 2-point function.
That's completely correct. Yes.
So, yeah.
But in terms of the first thing that people have already looked for is the 2-point function. And so that's entirely the reason why we're talking about the 2-point function. Is this is a search people have done before. It may not be the best search because it may be very, very non-Gaussian. But it is at least a search that has already been done by them. Yeah. And in fact, I think that might be the next slide.
Why is there a convergence for theta between 1 and 2?
We are not 100% sure, but we think this has to do with the fact that if you think about the last string in existence, there's a line through the sky that basically says the left half of the universe has a different polarization rotation than the right half of the universe. And we think that's why it sort of goes through 0 around pi/2 here. It's just that effect of the very last string. But you'll notice that the numerical one doesn't do that because it contains a circle instead of a line, where a line has a huge overlap with the dipole, right? It's left versus right, whereas a circle does not. And so we think that's just an artifact of how we simulated the strings as infinitely long straight strings.
Okay. So we shouldn't believe that.
I'm confused about.
We shouldn't believe that feature, right?
Yeah, we think at least that it is completely fake, that this feature.
I'm just confused by your explanation because the dipole is usually taken out, right? I mean,
So this has had no processing done to it.
Huh?
This has had no processing done to it. It's sort of just the truth level thing, and we haven't actually confronted it with how the CMB actually measures anything yet.
So you haven't taken out the dipole?
Yeah, that's correct. Okay. We have not.
Oh, okay.
Yeah. Okay, so let's see how the CMB actually measures.
But then I mean, if you do take out if you don't interpret the dipole as cosmic variance, you would get quite a bit smaller cosmic variance, no? Or is it really about the same? Do you know? I mean, that because normally you just interpret the dipole as just, it's not measuring anything. So you just sort of take it out. And so then the cosmic variance would be given by the quadrupole, and it would be less, a bit less, maybe not a lot, I don't know.
Yeah, so eventually when I compare it to data, I'm gonna actually Fourier transform this into CLs. And so then you just throw out the L = 2 mode.
Okay, yeah, okay.
And so in the end, that'll actually be taken care of. It's just, I guess in this plot, we decided to plot as a function of theta instead of L. Whereas in L space, it's very easy to throw out the dipole. And in theta space, it's not.
Right, okay.
Yeah. Okay. So let's talk about how the CMB actually looks for these polarization rotations. And I'm just going to give you a very toy description of how it does it, because people have worked very hard. I cited a few papers here who actually worked very hard to look for this effect. And so the way the CMB does this is they take E modes. So a polarization rotation, what it does is it takes E modes. So these are sort of divergence-like objects, right? Pointing straight towards the center, and turns it and gives it some curl. It sort of rotates it a little bit so that it is more like a line, like going sideways. And it does so in so as a nice way of getting rid of backgrounds, the effect I'm talking about is frequency independent. There are polarization rotations in the CMB that people have to, like from foregrounds and things like that, but it's all frequency dependent. And so people think they know how to subtract that off. So what they do is they take the standard Q and U parameters. So Q and U are basically how polarized it is in the X direction versus 45 degrees off of the X direction and things like that. So these are just the standard Stokes parameters for basically how you measure an electric field, its magnitude, Q, and it's sort of how polarized it is in any particular direction. And so a CMB polarization rotation rotates these guys. There's a factor of 2 because electric fields are spin 2 objects, right? If you take an electric field and you flip it by 180 degrees, it's still the exact same thing because it's a vector without a direction, right? Because it's oscillating back and forth. What you do then is you just take the 2-dimensional Fourier transform of the Stokes parameters, and that's what gives you the E and B fields. These are what I drew before, the sort of divergence and curl-like objects. That's actually what they were originally called, not E and B fields, but divergence and curl. You go through some messy algebra, and you can actually calculate what the B field is in terms of the E field. It's messy. All you know is, all that's relevant is that they're proportional to each other. And CMB people have done the exercise. So one of the CMB people's favorite things to do is to build an optimal estimator. So basically build the best possible way to look for an effect. And it turns out if you're focusing on 2-point correlators, it's simple enough of a thing that you can literally prove that your way of finding it is the best way possible. And so they go through that, do this, and what they do is, next one, is they get some plot like this. And so let's go over this a little bit slowly. So what they did is they calculated the CL, the 2-point function Fourier transformed as a function of L. And so here in gray, they have the bounds that come from the Planck data. So anything above this line is excluded. And then what they did was, the papers I cited at least, is they showed the projected bounds from the Simons Observatory or Lightbird. So these are basically 5-year timescale experiments. So in 5 years, they will improve on Planck 2015. Well, 5 years is when they start taking data. It'll be a few more years after that before they analyzed it. But on the 5-year timescale, these bounds will improve by about 2 orders of magnitude, you can see here. CMB stage 4 and PICO are more 10-year experiments, timescale experiments. And you see that they increase the sensitivity by about 4 orders of magnitude here.
These are the constraints. This is the vertical axis is some measure of the primordial B mode that you see in the 2-point function in the CMB.
Yes, that's right.
Right.
And in particular, the B mode that comes from being rotated from an E mode into the B mode. And
is the theory, maybe you're just going to comment on that, that you said that you have to subtract these foregrounds and people think they know how to do that. Is that gonna keep up as the bounds experimental sensitivity gets better, or is that gonna keep up?
That is a question that when I asked them, they said, when we take data, we'll know the answer to that question.
Okay, so maybe at least.
So the answer is maybe. There's no reason to say no, but there's also no reason really to say yes. So these are basically what happens if they can get rid of all their like instrumentic foreground instrument type noises. This is the ultimate sensitivity of these experiments.
Does that mean it's a little bit like dark matter? You know, if you exclude it, everything's great, but if you find a signal, you don't know whether you found a new background. Do you feel like
Yes.
it's a little bit like that?
It's a little bit like that. There are a
Yeah.
few handles here that you think you could get, for example, frequency independence and things like that. But even then, we've said all those same words for dark matter and then see where that got us. So I'd say the answer is if there is a signal, you'd have to wait quite a few years of astrophysicists arguing with each other to claim that they really have it under control. Yeah, but I think the way you said it is correct. It's just if there's an exclusion, you can definitely trust that discovery, wait a while.
Right. Okay,
So
cool.
how much does Faraday rotation play a role in this analysis?
So Faraday rotation is frequency dependent. So in principle, it can be subtracted. In practice, they have, it is not a limit currently. It's not an issue currently for Planck 2015. Whether or not that continues to be true, that's remains to be said. For example, I think like I said before, there's actually currently discussions because there's an anomaly in the polarization data. And there it's not, they don't think, well, it's either real or if it's not real, it's foregrounds. And so I think right now they're more concerned with foregrounds than Faraday rotation. But Faraday rotation is an effect that they actually do have to subtract off. It just seems like they're more concerned about foregrounds than they are about Faraday.
Yeah, I thought the idea there was that, I mean, of course, you're not just measuring better the B modes, right? You're measuring everything much, much better. And so this process that converts, you know, the E modes into B modes, you understand that better and better if it's part of the actual, you know, cosmic evolution. But of course, foregrounds, it's something different. It has nothing to do with making, you don't improve that a priori by making a better experiment.
Yeah. Yep, that's right. And so it's really up to them to see if they can actually do that. And yeah, they don't know, but they seem hopeful. Yeah.
So actually, sorry, just because I don't know, what are Lightbird and Simons? Are they satellites? Are they observatories on the South Pole, or what are they?
I think they're observatories on Earth, I believe.
On Earth, they're Earth-based.
I may be wrong. It's been a little while.
Okay.
I don't remember.
Lightbird is more like a balloon. Simons is on the ground. Yeah.
Okay.
Simons
there's a rule that the balloon experiments always give you anomalous results, and then they get superseded by some non-balloon experiment. Everybody says, well, it was a balloon experiment. So
yes, at least for dark matter, that's definitely the case.
Right. Okay. Anyway.
So I guess even for neutrinos, there's the Anita anomaly, which was a balloon. So yeah, I guess that's true even for neutrinos.
It's just it's just something, it's cursed. I don't know. Anyway. Okay.
I think like Simons will happen first though.
Yes.
So you don't need to worry about this.
Okay.
Yeah.
All right. Let's go one less talk I have to go to. So
yep. Yeah. Okay, yeah. But so these are the sort of projected constraints. This is the current one. And what we did was we took our numerical simulations and just plotted CL as a function for different values of C. So remember I said this is anywhere between 1 and 1,000. We don't actually know what the value is. And here I chose sort of electron type values of the Tuft anomaly of 1. And you can see sort of that, well, we didn't really trust our things at low L's. So we don't really know what we can say here. But for, let's say, C of 100, you can say, well, it's probably excluded right now. Whereas if you do the same thing, but for like down quark charges, like 1/9, then you see that it's something like 100. It's sort of not really visible currently, but can be seen in the future, especially for the 10-year time scale experiments.
Can I ask a very simple question?
Yeah.
So can you distinguish between gravitational wave background and they also have B mode, I believe, primordial gravitational wave, and
Yes.
this axion effect? In principle, can you distinguish them between them?
Yes, you can. I think the easiest way would do some position-based search of like literally just seeing if there is a string, literally like the left half of your telescope has a different polarization than the right half of your telescope. I think that would be the easiest way to differentiate them.
So sorry, Anson. Like gravity wave only give you BB correlator. It doesn't give you a EB correlator.
Yes, that's also true. Yeah. Oh, yeah. I guess these come from EB correlators, and EB, ET. Well, I guess really EB and BT are the ones that give the most strength, but I guess they use all the correlators. Yeah.
Okay, thank you. Yeah.
Yeah, I also just a very naive question. Why in these plots, why are you stopping at L equals 100 in these plots?
Because it's basically tiny. It's already well below the sensitivity at that point. So we just arbitrarily cut it off at 100.
Yeah.
I think actually the original people cut it off at 100 because that's where sort of Planck 2015 sensitivity was started to sort of fall off, where they didn't really understand things as well.
So how come Lightbird is getting more sensitive at high L's?
That's a good question. Why is Lightbird more
Large L,
sensitive at high L's? Like,
large L, yeah.
it must have good angular resolution, but why? I don't actually know the answer to that.
Okay.
Yeah, I think it's really like a suppression of like sensitivity at low L, not like enhancement of sensitivity at high L. Like
It's just the slope looks, it looks like a steep, if I look at the other experiments,
They're all the same slope.
they all look like the same slope, right?
one.
That's the anomaly there. So it looks, naively, it looks like at L
It looks
equals
like an
1,000,
enhancement.
Lightbird is gonna beat everything, right?
Yeah. Okay, so
yeah.
it does actually look like the difference is growing slightly here versus here. So it does look like maybe they do have slightly different slopes, but yeah, I'm not entirely sure actually. I mean, eventually the highest L is just set by your sort of angular resolution and things like that.
Right.
And I think they cut it off at 100 just because of Planck, not because of these other guys or anything.
Okay.
Yeah.
So are you gonna talk at all about, I mean, other things that people, I may have this wrong because I haven't thought about this, but I thought that, for example, other things that people wanted to talk about here are things like just additional light relativistic degrees of freedom, and these would also show up in these observables, or those, am I remembering wrong? Those are different CMB observables?
Those are different CMB observables. Usually ineffective, for example. Oh, I guess, okay, so it is true that polarization helps a lot with these measurements. And the reason why is completely different from this, which is that if you look at the CL correlators for the polarization data, it gives a better measurement of the peaks of the CMB. And so that tells you a lot more about, let's say, ineffective, like dark matter.
Okay.
And things
So
like
that's
that.
indirect. I remember there's some connection. Yeah. But are you going to talk about, let's suppose you see an anomaly. So do you guys get the Nobel Prize? Probably there's some other stuff, people that are in line for, I mean, there are other theories, other things that can give you anomalies in the B modes.
In principle, this is distinguishable from everyone else's, let's say, other people who have proposed B mode type stuff because of the sort of literal discontinuity, like the strings you could track across the sky. And so there is a way to distinguish this effect from basically every other effect.
Yeah. I mean, you know, I remember there were something, the thing that's the most like what you're talking about now that I can remember is, you know, people talked about these things like circles on the sky and things like this.
Yeah, like their hotspots and things.
Yeah, and my overall impression was that it devolved into a thing where, you know, once you identified some feature in, say, you know, position space, angle space there, it was sort of very hard to statistically justify it because you didn't sort of look for it in a blind way. You could see that it was there. And so anyway, what I'm saying is that it may really be very useful to sort of define ahead of time what that search is. Maybe not you guys, but, you know, it would really be useful to have it, make it, you know, explicit that it's an a priori, that you're doing an a priori search for something, not just, aha, see, I found what I was looking for, right? You know, like the 17 keV neutrino line, a lot of things like that where, you know, you focus attention on something that looks a little anomalous, but after the fact.
Yeah, that's right.
So.
Yeah, and so I think, well, we are talking with like serious people who will be sort of, who are basically doing something like along those lines of basically developing everything ahead of time without actually looking at sort of.
I mean, I think they were much worse shape because they were sort of by definition looking at low L things. They wanted to be like one circle on the sky or something. So then you're really screwed by sort of cosmic variance kind of
and
stuff.
So right? Here the statement is, let's say there's one loop per Hubble volume. So even though there might be one big loop now, you go to smaller scales, so further Z in the past, and you should be like, okay, now there are 3, and now go even smaller, and now there need to be 9, and go even smaller, and now there need 27.
Right. So I think you're in a lot better.
Yeah,
you're in a lot better shape, I think, than you are.
I guess, unless you're in the annoying situation where there was one string pre-inflation and it only just re-entered the horizon. And so it hasn't had time to like radiate and turn into many different strings. And then you'd just be like a line in the sky or something. And then you'd be very subject to the effects you just mentioned.
Yeah. Okay.
Yeah. So the take-home message from all of this is basically the sort of goal you're aiming for is sort of in reach in future 5 to 10 year timescale. Right now, we may or may not be quite sensitive to like electron charges. Okay, let's skip the power spectrum. It's not particularly important. I guess Curly will talk more about edge detection, but just very brief. It's what I think is one of the cool features because it's this position-based search. What we did here was we just took a line through the polarization rotation map. And you can see that every time you cross a string here, it jumps. We normalized it to the jump to be 1. And you can sort of see that here that it's just jumping along. And so if you have good enough angular resolution and good enough accuracy, then you'd be able to just resolve these jumps and even small scale, sort of small field of view experiments, let's say like BICEP, SPT, Polar Bear, Keck, or any of them. So interesting because it's also not being done. And so I can't really give you a bound coming from these searches because it's a search that's not being done. And so maybe it's actually sitting in there, the data, who knows? Okay. Let's see, I'm sort of over time. But just very briefly, another way, if you actually know where a string is, that you could look for the string is basically you can literally do something that's sort of like the Aharonov-Bohm thing where you can take a quasar and have its light, if it's strongly lensed, its light could go to either side of the string. And so you visually form the whole loop around a string. And you can just say, with strongly lensed quasars, can we actually see anything? And you can go through, there are only of order 100 some strongly lensed quasars. They can actually have a pretty large angle here. But you need the probability that the string is actually in there. And so you see that the probability is not super high. And so if you see a string, then maybe you could hope that there's a quasar nearby to try to look for it a second time. But in practice, you have to get a bit lucky. Okay, so let's finally, since I'm a bit over time, just say, well, very briefly, the way people normally look for strings is sort of these deficit angle approaches, and they look for it in the temperature data, where you literally just have a line around the temperature data. However, this depends entirely on the mass of your string, right? It's a gravitational effect. And whereas the effect I'm talking about here is more like the charge. It's like a completely orthogonal direction. And so anything that's not excluded can be in principle probed with these approaches. So what the final plot will look like is something like this, where you have the Tuft anomaly, which is what we want to measure, and the number of strings per Hubble patch, which is something that in principle numerical simulations will tell us. So in principle, at some point in the future, they'll be like, maybe this is the line you draw through this plane. And then there's just one parameter that you're looking for. You have sort of current experiments, Planck, future experiments. You can even look for the axion radiation being emitted by these axion strings that actually exclude some region of parameter space. Quasars can chop off a little bit. We have no idea how these sort of edge detection type algorithms will work. Hopefully they'll be good. So yeah.
Okay, I'll wait. I'll ask after. Go ahead. But finish. Why don't you finish up your?
So just to conclude, strings plus this sort of Tuft anomaly, sort of topological coupling, is to me a really interesting thing, because it's a direct way of measuring Tuft anomalies. And Tuft anomalies are exciting because it's correlated with the sort of quantization of electric charge. And so there are sort of multiple ways to look for it in the CMB. There is one, the standard way of doing a power spectrum type correlator, and another, which is sort of looking for in position space for these edges. And to me, this is exciting just because this is not a search that's being done. And so sort of talking to CMB people, they seem like they're actually, basically every CMB stage 4 person I've talked to has wanted to learn more and to see, can they actually implement this in for their searches, because more physics cases, the better for them. So, all right, thanks.
Let's unmute and clap for the talk. Okay, questions? So we asked a lot of questions during the talk. I have some more, but I'll save them. We usually, after the recording stops, if you have time to hang around a little bit, Anson, that would be great. We can
Sounds good.
Continue the conversation. Anybody want to pipe up before we do that?
So before your time, back in the day, QCD people used to argue about pi naught to gamma gamma, whether that measurement told us the charges of the quarks. And the sad fact was that they couldn't agree, but clearly it did.
Well, I mean, what it did was it told, right, because what that anomaly actually tells you is something about the sum of the number of quarks times their color. And so it doesn't actually tell you the real value. What it does, for example, tell you is that I think that there were integer multiples of 1/3. Because I think the quark value was 4/9 or something like that for pions. I can't remember exactly. Maybe it was 5/9.
But if you didn't know that the gauge group was SUN.
Oh yeah.
What was the issue? I mean, why do you say they couldn't agree, John? I mean, I thought there was like, there's SUN versus SON and whatever. You know, there's that kind of ambiguity, but the idea that it was a discrete thing, I thought everybody agreed on that.
Well, you'd have to talk to these guys who still don't agree about it.
Really?
Who disagrees?
Mike Tepper.
Mike Tepper. He's
Oxford.
not a dummy. He's a lattice guy. He's a smart lattice guy. Okay. Anyway,
interesting.
I don't know about this.
Yeah. Like, I mean, there are additional subtleties here that, for example, the axion famously mixes with the pion, and so obtains actually a fractional coupling to the photons from this. And so then you can ask, well, what happened to this quantization condition there? And what it turns out is that an axion string has a pion string exactly on top of it, because the vev of A determines the pi zero vev. And so on top of an axion string, there is always a pion string, and that rotation cancels between the two. And so you actually get the original coupling of the axion to the photon without any mixing to the pions. So unlike many of the experiments looking for the axion coupling here, which actually includes the mixing with the pion, this is actually a measurement that doesn't have that sort of pollution built in.
Cool.
Yeah, and so that's that was fun.
What is it that picks out the axion versus the pion then? I mean, in the Lagrangian, it looks like, I mean, they have different decay constants. I understand that, right? But besides the value of their decay constants, what distinguishes them?
I think strings are sort of objects that live on the charge lattice, not the mass basis, right? Because the mixing is sort of a mass basis thing, whereas this sort of strings are objects that live sort of like monopoles more on the charge basis, and that rather than any mass type effect. And so just, I think their very nature sort of picks out, yeah.
Right. So it's not really picking out the axion versus the pion. It's more that it's an intrinsic effect, electromagnetic effect that's sort of independent of what field is there. And somehow with the pion, your A is now some mixture of the pion and the axion, but who cares? It's just like the fact that this is independent of F, you know, it's the same effect, right? If this A was really a linear combination of axions, everything would presumably go through.
Yeah, everything goes through.
Yeah, I get it. Okay.
These anomalies are just remarkably robust.
Right.
Which is nice.
All right, any other questions? I feel like I interrupted the talk enough, so I'm saving mine for. Okay, well, let's thank Anson again. And like I said, I hope we can continue the conversation a bit.
Yeah.